Welcome to the next video in the stochastic calculus. This time we will discuss martingales and their quadratic variation. All right. So what we have seen in the last video was that if we want, if you have a continuous martingale which is locally of finite variation, then it's a trivial martingale. So then it's constantly equal to its, almost surely equal to its initial condition. So this is not a good starting point to develop any stochastic integration theory. And now we want to consider instead the quadratic increment. So of considering the variation process, which was our martingale will be denoted by x of martingale xt. We want, or we consider, we want to consider the increments squared, right? So take our partition, which let's say pi n, and now you recall, if I consider the increments to the absolute value of the increments, where I get the finite variation, or the variation process, and now I make here a square, right? So that's the new thing I want to consider in this lecture. Okay, and I want to consider this along any or some zero sequence of partitions. Yeah. All right. Okay. And recall, if you have a non-trivial martingale and you make here 1 and take the absolute values, this explodes to infinity. And now we consider instead of the square increments, and the hope is, well, that this converges to something finite. And this is actually the content of the next proposition, which is position 2.15. Okay. All right. Okay, so for simplicity, we consider a martingale which is bounded. Because we will extend this proposition later on anyway, so we don't need to take the extra work to consider general martingales. So we take a continuous martingale and we assume it's bounded. What does it mean? So what is a bounded martingale? Well, this means if you look at the absolute value for almost all omega, this is less to some constant for some c, and all t in our interval for almost every omega in omega. Right, so almost surely I am bounded over the whole time interval by a constant c. Okay, so that's, but the boundedness assumption I'm just making to make my life easier, and later in the course we will drop it. So we will see that it's not necessary. Probably in the next video. So what's the statement now? And then there exists a continuous stochastic process, which I denote here by this bracket process x. Okay, it's a stochastic process as usual, so it's indexed with our time interval 0 to t. Such that, so it has the following properties. The first one is, well, xt is given as limit, n goes to infinity, of the square increments. So this in particular means this limit exists in a reasonable way or a meaningful way. Just uniformly and on 0t, and the convergence takes place in L2 for any zero partition. So you can take any zero sequence of partitions and they all converge to this bracket process of x. Partitions. Okay. Okay. This is the first property this bracket process fulfills. The second one is, okay, if you have this, you won't be surprised. So it starts from 0. So times 0, this is just 0. And x is non-decreasing. Okay. And the last property is, if I look at the x to the power 2, so the square process here of x, and I subtract this bracket process, so this, then it's a Martingale again. No, Martingale. Okay. Towards the issue, I mean, if you take the power 2 of a Martingale, what you get is, I think it's a sub-Martingale by the conditional Jensen's inequality. So the conditional version of Jensen's inequality tells you, okay, if I take the Martingale and then I take it to the power 2, I get a sub-Martingale. Now, so you need to compensate it by something non-decreasing in order to restore the Martingale property again. And this is exactly this bracket process. Okay, so let me make this to a definition. We will refine it for a more general class later on. So the process, this bracket process, x, is called quadratic variation. Called quadratic variation of x. All right. Okay, so this is what we want to prove in this video, is that there indeed exists such a process. So we need to show that this limit here of the square increments really converges. And then I want to convince you that it has the 3 properties. So it starts from 0, which is rather obvious. It's non-decreasing. Okay, that's also not too hard. And the limit is a Martingale. That's the main work. So the main work is to show the convergence and then that this third property telling you that we have a Martingale. All right, so let's do this. Proof. Okay, first thing I would like to convince you, without loss of generality, we can assume that x0 is constantly equal to 0, right? Why? Well, otherwise, consider x tilde, which is given by xt minus x0. So this doesn't matter, so we just normalize it that x0 is 0. And to make my life simpler as well, we assume that t is finite. Okay. Otherwise, you need to do it locally. Okay. Okay. Cool. Okay. So what do we define? So we define the following process, which is AT. Right. So I mean, they can also make it here part of the statement. Okay. Okay. Let's okay. So what we do is we label the discrete quadratic variations, or the sum of square increments over the partition pi n as an. Okay. Work. Cool. And the first thing we want to show is that if I look at the process, let's call it nn, which is x to the power 2 minus an, then this is a Martingale. Okay. First. So what we see, if we compensate, let's say, the square process of x with this sequence of an, we already get a Martingale. And then we just need to show that the limit process exists, and this is a Martingale as well, which we follow from this Martingale property. All right. Okay. So let's do this. How do we see this? 16. J. T, which is, right, so they use a telescoping sum argument to express this x at time t to the power 2 by along the sequence pi n, or this is pi n, sorry. And then, okay, let's normalize it t, but you cut off the moment you're bigger than t. So all summons which are bigger than t, I mean, all they disappear. Right? This is a telescoping argument. And now you use binomial's formula to rewrite this as 2 times x at the point sj multiplied with the increment of x t minimum t minus xj minimum t plus xtj minus sjt to the power 2. Right? Why do we want to do this? Because, well, what you see here, if you have a look at the sum and the second summand here, you get your process an. Right? So that's good. This is what we wanted to recover. Right? So this is nothing else than twice the sum from j elements of pi n of x j2 t jt t plus an. Okay. Yeah. And now what we see is, okay, if we rearrange this, so an, right? An was x square, which is the left-hand side here, minus an. So we put an on the other side. So an is just given by this first sum here. So twice j tj c, and so this is just copy pasting the line above. And my claim is now this is a Martingale. How do we see this? Well, okay, we need to check it. So what we want, what do we need to check? So we look at the conditional expectation of nn at time t minus nn at time s, and we restrict it to the filtration at time s. And if this an is a Martingale, this has to be 0. So we need to check that this is 0. Well, okay, so let's calculate it. We know what it is. This is twice. We'll look at the sum here, the definition, or the equality we just proved. And then we sum over all j in pi n, where pi j is greater or equal s. Why do we do it? Because everything which is smaller than s, I mean, it's just here. I mean, we just subtract it from each other. So these sum and disappear because of this difference here. Okay, that's good. And then we have the expected value, or the conditional expectation of x j, right? Then here multiplied with the increment from tj t minus sj maximum s t s, right? And everything conditioned on fs. Well, this is what we have here. Okay, so that's nice. How do we see that this is the 0, right? So let's pull it out a bit further. So we have still the sum here, tj very bigger than s. And now we use the tower property to sneak in the conditional expectation of sj. Right? Because if we put here conditional sj maximum s, then we have this. So what we have in here is the jt minus xj t. Wait, okay. Now we have it done. This is just copy pasting. And now this is a Martingale. So x is a Martingale. So we know that this is 0 as x is a Martingale. Okay, that's nice. So I mean, all in all, for every summand is 0, this means this is 0 as well. Okay, and this holds, of course, for all s bigger than t in our interval 0 to t. Okay, that's great, right? So this is a process starting from 0, and it exists because it's the finite sum. And if we compensate the x square with this an, we have a Martingale. So the only problem is that this is not an increasing process. And we will later see that the increasing part is, I mean, we want to have it in order to have a uniquely defined quadratic variation. But this is for next video. So note, n might be not increasing, or well, so not monotone. Okay. Because if you look at the between two partition points, you might have a fluctuating process. That's it. Okay, so we want to go to the limit, and this is what we do in the next step. Second step. Show that if you look at the limit, let's say m goes to infinity, and we look at the supremum over all n bigger or equal than m, and then we take the convergent uniformly t, and we look at the difference of an m. So this is an m, sorry, that's important here. This is an n to the power 2. This goes to 0. Okay. Okay. Again, let me make some simplifying assumptions. So tiers, part of the partition. Is the partition point. Of Pn, m, and in particular, this means for all bigger one. And we set Jn to be all the intervals which are in this interval. Okay, right. So, okay, since you can think of we work with a finite interval, so then it's all not a problem. So this is the only reason why I have to play around here is that I allow an infinite time horizon. So otherwise, if you think about a finite time horizon, okay, that's all clear. There's nothing to do. Okay, so let's estimate. Note. Let's estimate the supremum from 0 to t. Right. Right, and we have already learned how we can estimate the supremum of Martingale. I mean the running supremum of Martingales. Well, this was Dup's maximal LP inequality. Oh, maximum. No. Let me. Okay. So this is just 4. I mean, this is p is equal to 4. So this is nothing else than the difference at the terminal time to the power 2. Okay. All right. So let's plug in the definition. We know what the difference of two n's is, right? This is the definition of n. So we get here another factor 4. So this is 16. And then we have the difference. So let's plot this in. Right. Xj, xjk multiplied with the increments in xk, right? So what we do is they are refining. Let me draw a picture, then you can see easier what I have done here. Right, so you have your interval, which is which is the bigger one, which is an m. So this is j and j, t, j, and now you plug in. Well, here's some partition points, which are your case. K1, K2, K2. This is the finer partition. And since this is refining, oh, this 3, 4, 5. Okay. Okay, so this is just spelling out what it is. And now we multiply this out. And this is a martingale, the cross term disappeared. I mean, we will make this argument again in a minute. So point is that this J and K. Okay. J K power 2 and then power 2 of the K argument. All right. And now we use, for example, Cauchy-Schwarz, but okay, you can also use other inequalities. So this is Cauchy-Schwarz inequality to estimate it by supremum here over all J in M and another supremum over all K's which are part of J and in the next level of Jn. Right, maybe it's 1 square. And then you have here the second summand. So this is J over K X, sorry, the delta over K square power 2, and then square root of it. Okay. So we have now two terms we need to treat. Let's call this 1 and this 2. And let's estimate it. And we want to show that this goes to 0, right? This is the claim. And how do we show the claim? Well, we want to show that, okay. What we want to show is that the first summand at this first in the element of this product goes to 0 and the other one is bounded. Then we're done. Okay. So that's actually not so hard since we have now our dominated convergence. So this is the first term, J and Gem, J and all J and K, which include N and J and K. Right. But, and here we can now use dominated conversion and the continuity. So X is continuous plus the dominated convergence theory. So this is why I want to, for simplicity, the assumption that my martingale is dominated, because then I can pull in these limits without any problems. Okay. Right, 1/2, this is not important. This goes to 0 because, well, if you look at here, this year, they go to 0. That's good enough. All right. Let's come to the second term. For the second term, okay, well, recall, there exists a C such that for all T and T and P almost surely. Okay. All right, cool. So let's start calculating this. jk, jn. Yeah. So that's the second term we want to calculate. Well, this is okay. Let's calculate this out. So this is the sum over j, k, and well, x power 4. Well, if you, now we get some extra terms, which are twice. Well, this is binomial's formula. So there's not so much going on here. So we get here the sum over all n, and then the increment twice, and now with the sum over all k in jn, such that, okay, right, we order them a bit. J, well, that's the j. All right. Okay. All right, let's estimate this. So the first one, okay, what do we get? I mean, okay, we can estimate it by 4k square, right? So we can estimate every increment by 2c, and then we get 2t square if we have the square. And this means we have not estimate all things. So what we have here, we have still the sum of over the elements of Jn of x to the power of the square increments. And let's sneak in here a conditional expectation by the tau property. So Jn and multiply the increment of x, and then we sneak in here by the power property another conditional expectation for the j. So this is again copy pasting and then restricting to j. All right. Okay. Okay. So from here we still not see that this is bounded. So we need to do a bit more. First thing is, since x is a martingale, what we have, well, we know that if we look at these terms here, so if you look at the conditional expectation of the increment along the x, along k, or 2, and then restricted to the filtration of tj, that's nothing else than, okay, this is binomial's formula. Right? J. And well, that's great since we have a martingale. So this is where we use the martingale property. We have that this is t. This term is nothing else than twice the last one. So we get here minus x to the power 2 at time sk. So that's where the Martingale property comes in. So we get that if you look at the expected value of this sum which we want to bound, And now we use the estimates we had before. So we have 4k 4c squared, right? This is, sorry, this term here. And now we use this extra calculation here. So the increments becoming just a scaloscoping sum. So what do we get here by the, again, tower property? Means just we add the increments of the expected value of x squared at x minus the expected value of x squared at sk. Okay. Okay, that's actually easy. What is it? This is nothing else than x squared at time t. Again, a telescoping sum argument, right? And now we forgot still the second term here, right? This is this term. So what do you get? Same argument. So we get the sum over all j and jn of increments along j square multiplied with the expected value, the conditional expectation of xt square minus xtj square conditioned on f at time tj. Okay, and this can be, I mean, the difference we know how to estimate, so we can estimate this again, my 4.2 square, right? This is the first one, was easy, plus c squared. And we can estimate this, and then we have just the sum over all jn, right? So we estimate this here in absolute values. So check the absolute values here. Oh, here's a bracket missing, right? Sorry. By 2 c squared. Okay, and then we have still the sum over the increments, square increments of x along jn. Okay, this can be, well, this is nothing else than 8 c2 x. Okay. All right, so this is bounded. That's great. Okay, cool. So this means we go up here. The first one, the first term in the product goes to 0, and the other one is bounded. Cool. All right. So we have convergence, and now okay, we need to ensure the existence of the convergence. So step 3. So now we need to collect all the properties. Okay, due to step 2, we have that we can define the limit as n goes to infinity of Sn uniformly on 0t in L2. Okay. This means, well, there exists a subsequence, right, such that the subsequent, if k goes to infinity, goes to n uniformly on. Okay, so what does this mean? N is continuous, right? Because it's the uniform limit of continuous functions. I mean, the temporal paths are continuous. All right, so that's the first thing. Right? And this n will be, right? N is just. Oh. So now we need to check that n is a martingale. n is a martingale. Okay. Which is equivalent to say, well, if I look at the expected value of n, this is n, and I condition it, well, on a set, indicator function of a set A, where A is in Fs, this has to be 0. But this is just by the definition of the conditional expectation. Okay, so let's calculate this. Well, how can we see this? Well, we take the absolute value, I mean, of this conditional expectation we want to estimate. Right, because then we can estimate it from above. And now we sneak in our approximating sequence, for which we know it's a martingale. So we have sneak in here the approximating sequence in K, right, plus nkt and ks. Right? This is adding and subtracting a null, 0, plus, minus, sorry, to have the signs right, s, k, s. Okay. Right? And this is 0, since this is a martingale. This is what we would determine in the first step, is a martingale. Okay, oh, I forgot absolute value here. That's great. So we can now estimate this by absolute value of nt minus ntk, right? This is the first one. Absolute value, indicator function of A. This term, the second term disappears, and the last one is of course still there. So we get it again. T. Yes. Okay. And now this goes to 0 as k goes to infinity, because the k and k approximate uniformly the martingale, the process n. So this is a martingale. Okay, and well, this is my Fatou's lemma, right? Because we need to interchange integration and limits. Okay. Oh, sorry, this is actually wrong. Sorry, my side comment was a bit wrong. So now we define x in the bracket process x, or the quadratic variation, xc as x squared minus n. Okay, and now we know x is continuous. Well, because n and x squared are continuous, it's adapted, because well, the other processes are adapted as well. And it starts from 0. And finally, if I look at x squared minus x, the variation of x, this is just n, so this means it's a martingale, which we have just shown. Okay. Okay. So the only thing we need to still ensure that it's increasing. And last thing is, or non-decreasing, because it might be right. On decreasing. Since, okay, that's not a hard calculation. So if I look at x at time t, this is nothing else than the limit n to infinity of the square increments, right? This is where it was coming from. Oh. Jn t x squared. Well, now, okay, if I take an s, so t and s is less, we have, well, this is nothing else than limit n to infinity of the increments up to time s. Right here is up to time s, plus, well, the limit n to infinity of n, which are only the increments from s to t. Okay. Square, and this is certainly not negative, so this is greater as x. The quadratic iteration at time t is greater or equal than the quadratic iteration of time s. All right, so that's it. So we have shown that the quadratic iteration of a martingale exists. So if I take the square increments instead of the increments, then they converge. So if I take the limit along any zero sequence of partitions of the square increments of a martingale, I get a process which is well defined and has nice properties. All right, and thank you for watching the video.